Hi everyone, welcome to AND 310 session titled How VMware Uses Amazon Kinesis to Keep Their Customers Safe from Cyber Attacks. My name is Sai Madali and I have with me today Devor and Corey from VMware to share about how they use Kinesis data streams. What we're going to do before we dive into how VMware uses Kinesis is we're going to start with a quick overview on streaming data, talk about some of the key KDS capabilities, and some fundamentals on how you program using Kinesis data streams APIs. Let's get started with an overview first. Now, the reason real-time streaming has come about is we all want to respond faster to our customer needs. Survey after survey, users such as chief marketing officers tell us that how critical it is to drive instant insights to improve the overall customer experience. This means now you want insights in seconds and minutes, not in hours, weeks, and months as it was in the past. Let's understand this with an example. Say you're an e-commerce company a decade back, and you're an e-commerce company and you want to provide discount coupons to your loyal customers. Now, a decade back, the way you would do that is you would capture all the data in your transactional systems. At the end of the day, or maybe sometimes at the end of the week, you will run an ETL job that would extract this data, transform it, and then load it into a data warehouse. And then you would actually go run a report that will identify who your loyal customers are. And then you send them in a coupon over email, hoping that they would open that email and then obviously get value out of it. Now, this is a hit and miss for a lot of businesses as we have known in the past. Now, with streaming data in real time, what you can do is provide that coupon to the customer right when they're doing the checkout of that product that they're trying to buy. With this, you're able to improve the overall customer experience, increase retention, and loyalty. This is just one example. The need to respond in real time exists across various domains. It could be about collecting data from mobile applications to provide real-time notifications, like the example that we talked about, or it's about collecting, storing clickstream data from websites, mobile applications, and so that you can provide a feedback loop for real-time personalization. Imagine you're developing a game. How valuable would it be for you to capture how your users are responding to your game and be able to tweak that in real time? Now, we're going to see later in the presentation a use case around how VMware collects sensor data to perform things like anomaly detection to safeguard their customers from cybersecurity threats. That's again another use case where real-time insights are important. Or it could be IoT use cases where on the shop floor where you have different machinery which has a bunch of sensors, you want to collect all the data and do things like predictive maintenance right within the shop floor, thereby improving the overall productivity. Or it could be smart cities, smart metering. Now, one thing that is common across all these use cases is you really want to drive insights in real time, which is typically within seconds or within minutes. Hopefully, some of these use cases resonate with some of the business problems that you're looking to address. Now, what customers have told us is the ability to apply streaming data is across different use cases. However, it requires a lot of hand-holding to build the right set of infrastructure to address those use cases. Now, you need to first select the instances, benchmark them, test them, make sure it addresses your workload needs, ensure that you're designing it for high availability, high durability, because obviously you want that to be a mission-critical application. And then you have to muck around in terms of how you scale that infrastructure as your business grows. That's a lot of hand-holding that you got to do with the infrastructure, which is precisely why we built Amazon Kinesis Data Streams. So let's talk about how Kinesis Data Streams helps customers build streaming data platforms. The first principle is it's easy to use. You don't have to provision servers or VMs or containers. All you do is log into the console, create a stream, and provide what your throughput requirements are, what your workload needs are, and then you get assured capacity within minutes. It's not only easy to get started, you can scale that stream with a few clicks, and that is where elasticity comes to the fore. So you can scale up as your traffic patterns change or increase. As you have more customers using your product, you can scale up capacity. Or if you see you don't need as much capacity, you can always scale down to save costs. We're going to see how VMware uses elasticity at its core to drive their streaming data infrastructure. Kinesis Data Streams stores all data durably in 3 different availability zones and provides a 99.9% SLA. This gives you the peace of mind to run mission-critical applications without requiring additional handholding. The fourth key benefit is the seamless AWS integrations that Kinesis Data Streams offers to customers. Now, streaming data systems do not function in isolation, right? You have a bunch of producers that are producing data. You have to capture that in a streaming data platform, and then you have a set of consumers that have to process that data. Now, let's see how this integration helps with our e-commerce example, right? So I've built an app. Now I'm capturing all my transactional data in Amazon DynamoDB. With a single configuration, now I can stream the data to Kinesis Data Streams, use AWS Lambda to write a quick function, and basically write my business logic on how I want to generate this real-time metrics. As you can see here, I'm not worried about servers. I'm not worried about provisioning, capacity management. I'm just focused on really the core business case that I have and how I can address that. That's where integrations come to the fore. Finally, given that you can provision the capacity that you need and you can scale up and scale down when you don't need the capacity, it really provides your cost-effective mechanism for you to operate your streaming data platforms. So that's in essence 6 key benefits and some of the capabilities that Kinesis Data Streams offers to customers. All right, so we talked about features. Now let's talk about some of the core concepts of Kinesis Data Streams. How do you program with Kinesis Data Streams? Like I said before, there are no servers to provision, right? So you create a stream and you interact with stream using APIs to write data and read data. Now, if we quickly go back to some of the use cases that we've talked about early in the presentation, all the real-time streaming data use cases, one thing that is common is you're generating vast amounts of data and you have to process that at a sub-second latency or sub-minute latency. You also have to future-proof this architecture because what your requirements are on day 1 may not be what they are in day 10. Your traffic patterns change, you're onboarding more customers, you are just basically growing your application and its needs. Hence, the core technical goal is how do we process large volumes of data at really low latency. To do this, you want to partition this data and take each chunk and process that so that you have end-to-end really low latency. Kinesis shards address this needs precisely. They also act as a unit of throughput. So with each shard, you get about 1 megabytes per second for writes and 2 megabytes per second for reads. Now what this does is it ensures that your consumers can be designed that they can process definite amount of data at any given point of time. So you are actually not falling behind when you have a sudden increase in traffic, and you can ensure that your insights are always fresh for your end customers. Shards also act as a unit of throughput. So if you need more capacity, you want to scale up your capacity, you would add more shards. Now, if you realize that you don't need that capacity, you can scale down by decreasing the number of shards in your Kinesis data stream. So that's what a shard is in essence within Kinesis data streams. Now let's talk about how do you write data to Kinesis data streams. When you publish messages to a stream, you specify a partition key, which helps Kinesis data streams group these records into individual shards. This partition key is typically a business key, whether it's a product ID, customer ID, and so on and so forth. Now let's see how KDS uses this partition key to route data to shards. Now all shards in a stream share the hash key space of 0 to 2 power 198, as you can see in the picture in the slide here. So if you have 3 shards, shard 1 would be between, as an example, 0 to 2 power 196, shard 2 from 2 power 196 to 2 power 197, and so on and so forth. So when you write data and you specify a partition key, Kinesis takes that partition key, converts that to a hash key, and depending on where it falls in terms of the shard range, it assigns the record to the appropriate shard. Let's again go back to our e-commerce example to understand this. Say you have a requirement where you want to show the last 10 most frequently bought products for your customers. Now, what you want to do is across all the products, across all customers who are accessing those products, you want to capture all that information, count how many times a product was bought by each customer, generate a stack rank, and publish that on your website. Fairly straightforward, right? And you want to do that within seconds and minutes because you want that to always be real time and not stale static data. Let's see how you do that, how you write data for that use case. Now, in this use case, you specify the product ID as the partition key. So KDS takes the partition key, generates the hash key. So in this case, you'll see that all the purple products are assigned to shard 1, all the green products are assigned to shard 2, and all the white products are assigned to shard 3. Now, this data locality is important for you to actually count these things in a very short period of time. If you have all the records within the same shard, your processing logic can access all these records within that same thread or within the memory and thereby able to perform these calculations very quickly. So you can actually scale your application regardless of how many products you're adding, regardless of how many customers you are actually serving, and still be able to generate the top 10 most popular products list to your customers in real time. So that's how you write data to Kinesis data streams. Now let's talk about how you read data from a Kinesis data stream. In Kinesis data streams, all the data written is appended to an immutable log storage. All the data is stored until the end of the retention period. The default is 24 hours. However, you can extend that optionally to up to 365 days. To read data, you simply specify a starting point and you iterate from it. It could be the latest, which is a last record that was written to your stream, or it could be from a specific timestamp. Maybe you want to read the last 3 hours of data, or it could be from the start of the retention period. So say if you have a 30-day retention period, you are basically processing 30 days worth of data. After you specify an iterator, you simply read through all the records in the exact order in which they are actually stored in the system. And every time you process a set of records, you checkpoint your progress. So as an example, you could say, hey, I processed the first 10 records. Now I'm going to checkpoint my progress. And the reason you do that is to ensure that you can build resilient applications and guard against failures. So say a failure happens. Now in a distributed system, you want to design for resiliency. So what happens in this case is you go back to your checkpoint and say, hey, last record that I processed was record 10. Now let me restart processing from record 11. This enables you to at least achieve at least one guarantees for your processing. So that's how you read data from Kinesis data streams. But the other thing that I do want to talk about is how shards also act as a unit of parallelism, right? So yes, you got all the data in shards. Now you have to process them, and you want to process them at really low latency. The way Kinesis enables you to do that is by creating a record processor, as you can see in this picture, for each shard that you have in your Kinesis data stream. So in this example, you have 3 shards, and I have one instance, which is called a worker in Kinesis data streams, and I have 3 record processors. Let's imagine I'm bottlenecked by the memory on that or CPU on that instance, and now I just want to scale out and add more capacity. The way you do that is you add a new instance, and then as you add more instances, they coordinate among each other to share work. So as you can see here, the record processor 3 gets transferred from worker 1 to worker 3, and thereby you're able to process and scale quickly and ensure that you're able to deliver insights at really low latency. So that's to recap real quick. You use a partition key to write records. Kinesis uses the partition key to route records to specific shards. That data locality and the shard's parallelism enables you to process this data at really low latency. In essence, that is how you write and read data into Kinesis data streams. Okay, so one other key benefit of streaming systems is you can attach more than one consumer. So in our example, in an e-commerce example, you have one application that is providing real-time insights to customers. It could be a marketing application. But then you also want to attach a new application that sends the same data to a data warehouse so that you can understand your buyer behavior, you understand your customer behavior in terms of what purchases they make, and so on and so forth. Also, you want to attach another application now that takes the same data and sends it to a financial system where you're doing things like accounting as such. Right? So here you have the same data that you're capturing, but again, the processing that you're doing is very different. When you do this, it's very important that you have certain levels of isolation between all the different applications. Well, you can't tell your marketing team or your financial team that, hey, the marketing application is basically trying to process more data, so hey, can you just wait for a bit, right? You need to ensure that each application or each consumer can process on its own, essentially. Kinesis Data Streams delivers this capability using enhanced fan-out consumers. When you use enhanced fan-out consumers, each consumer gets its own dedicated bandwidth. So the performance of one application has no impact on the other. And you can use this capability to add up to 20 parallel consumers, with each having its own dedicated throughput. EFO not only provides you, dedicated throughput, but it also enables you to do low latency reads from Kinesis data streams. So if you have a latency sensitive application, say if you're using Kinesis data streams to send data between one microservice application to another microservice application, you want to make sure the end-to-end latency is low. In this case, enhanced fan-out becomes extremely useful. So I briefly touched upon this. One of the key benefits of Kinesis data streams, and you're going to see that with the VMware example as well, is the ability to scale up and scale down capacity pretty quickly. Now, like we discussed, each shard owns a hash key range, and the data is routed to them based on the partition key that you supply. Now, you may get a question, what happens if more than 1 megabytes per second of records are routed to a single shard? How do I address that? Now, Kinesis Data Streams makes that easy by providing you the ability to split a shard. So in this example, I have two shards, so I have 2 megabytes per second for writes, 4 megabytes per second for reads. And I want to split shard 1 to ensure that I can double my capacity, as well as shard 2. So in this case, what I do is I take shard 1, split it. So now I have shard 3 and shard 4. I take shard 2, split that, and I have shard 5 and shard 6. So with very simple operations, I'm able to add capacity very quickly. We also provide you an API called Update Shard Count that allows you to simply get to a target shard count. So say if you have 2 shards, you want to get to 4 shards, you specify the target shard count, and Kinesis Data Streams automatically scales that stream to that particular shard count. So you've got 2 approaches here on how you scale up capacity. You can not only scale up capacity, but you can also scale down capacity. You can choose 2 adjacent shards, in this case shard 3 and shard 4, and basically use a merge operation that now combines these 2 into a single shard. When you do a split or a merge operation, existing shards are closed and new children shards are created, Like before, you can also use the Update Shard Count API to scale down to a specific shard count. So to summarize, with Kinesis Data Streams, you don't provision infrastructure for ingesting data. You provision a stream and interact with APIs to write and read data. This enables you to build highly resilient and scalable applications for your streaming data needs. Now, with this knowledge, let's now look at how VMware uses KDS. Now let me welcome Devor from VMware to talk about how they use Kinesis Data Streams for their use case. Take it over, Devor.
Thank you, Sai. My name is Davor Roglic. I'm architect at VMware Carbon Black. So challenge we faced was to build an enterprise EDR solution in the cloud. First of all, let me explain what EDR is. EDR stands for Endpoint Detection and Response. It describes technology used in security space for recording endpoint behavior and responding to malicious activity. The job of security analysts is to be a detective, to follow the clues of unexpected and intentional amongst the noise of normal and expected behavior. And sometimes he or she doesn't know what exactly to look for in the first place. So therefore, the job of EDR solution is to painstakingly record every file modification, every registry change, every network connection, every process start, and so forth. This allows analysts to search through the data in a free-form text search. This search has to be fast. As you can imagine, a given amount of data involved, analysts will have to do many of these ad hoc searches in a rapid sequence before zeroing down on a threat. Once they find the malicious needle in a haystack, the solution also needs to provide them with the way to automate this search, right? And once it's automated, also to alert customer that something is going on. And finally, we have to do it at a petabyte scale, at the millions of endpoints, and in the cloud. Now, before we even started building this solution, we had to decide on an important architectural aspect of it, which is tenancy. We could have gone with a single tenant solution. We already had a solution like this in our on-prem, and customers liked the solution, and we knew how to scale it and how to manage it. What you end up is basically a separate stream for each sensor and data stream that carries the data for each sensor into these separate storage engines, right? Into the separate search engines, and customers accessing to the separate APIs. Could you just lift this solution into the cloud and provision one instance of architecture for every client? It's possible, it's not unheard of, but there are a lot of downside to this approach. There are some positives as well, right? So let's start with the positives. The performance of this solution is typically good. You provision each instance according to tenant size and basically add more hardware when needed. Your customer gets more data, maybe you add another node to the cluster. There is no interaction between the tenants, which provides both performance, reliability, and easier to achieve security. Downside are related to complexity of the solution. Now you have to manage thousands of individual instances of the architecture. It's, you can say, operational nightmare. Even without added operational cost, there is no resource balancing and sharing. So your final hosting cost will typically be much higher due to over-provisioning. And finally, if you have to do any kind of integrations with your solution, you will have to plug into each individual API, and there is no way to do the cross-tenant searches. The second option is pure multi-tenant solution, right? This is what most cloud applications are built, the way they are built. On the ingress side, incoming data is sent into the shared infrastructure, and it's easy to scale in or out. Similar is with the storage. Its capacity is shared, and it can compensate for temporal fluctuations in load in ingress, and also search for individual tenants. This ends up with a much lower hosting costs. From the operational perspective, it's also a simple solution, right? Because it has smaller number of services and fewer scale in and scale out points. Integrations are easier because there only is a single point where you need to plug in. Hosting and operational costs are lower because you have less infrastructure to manage and better computational and storage efficiency. There are many downsides, however, right? It's because your individual tenant performance will be much less predictable. If, for example, a couple of large tenants start sending much more data, they could back up the entire solution for other tenants. Also, if a single tenant starts running a lot of more search queries, it could impact search for other customers. There are also basically problems with data isolation as well, right? Because each customer data is stored together. So it's really difficult to provide perfect safety around maybe SQL injections, right? Or any kind of even bugs in the code could mistakenly reveal the data from the wrong tenant. So you have to be much more careful. And finally, retention of this solution is kind of very difficult to manage on per customer basis, right? If one customer wants to have a longer data retention, meaning maybe keeping 3 months of data versus another customer that wants to keep 1 month of data, you have to start deleting the data very selectively for tenant, which can be very expensive. And finally, after analyzing both of these, we actually decided on a hybrid solution. We use multi-tenancy, but with the tenant isolation at the indexing and the search layer. There is single index stream that can be easily scaled in and out, but at some point we separate data into physically at the storage layer, which simplifies and makes sure that search performs well and the data is isolated. This kind of checked all the boxes for us. Let's dig deeper into that. When you think about that, the main challenge is to take completely randomized data from the ingress stream. You can think of it as a high entropy data, and then partition that data into individualized tenant buckets. So what you need to do basically is it's entropy reduction, right? Now, entropy is not all bad, right? High entropy data allows you to treat all the data the same, right? That's kind of a definition of entropy, right? You can look at the whole system, without understanding the little details. So it's easy to scale in and out by just scaling in and out the stream of the data. This is something that Sai was mentioning in his part. Now, it's much lower maintenance. However, as we said, at some point we want to partition the data and lower the entropy, right? And to achieve other architectural goals we had. Let's see how we did it in practice. When you look at the incoming data, it has some per tenant volume, right? Some tenants are sending more data, some are sending less data. If you could just add different resource amounts for different tenants based on this data, you could solve a lot of problems, right? So we can think of that as like a logical partition of the data, right? Based on the incoming traffic, we assign more or less logical partitions to each customer or tenant. Now, how do we transfer this logical partitioning into actual physical partitioning? Because that's what we ultimately need. We need to physically store the data into separate data stores. The answer for that, for us, was Kinesis, right? So we use Kinesis Stream to do that. We utilize the main feature of Kinesis, which are physical shards, right? So each shard will map to the corresponding logical partition, and each partition is going to have the same bandwidth and the size. This ultimately ensures that each shard is approximately equal, produces equal size index, and we can benefit from that downstream. So once the data is passed through the second stream, which is partitioned, the bandwidth allocation that Kinesis has forced on us ensures that the indexing process will also produce similar index sizes. This allows us to allocate compute resources that will always host similar indexes, and which is much easier to manage. They're basically fungible. We can then keep adding resources or containers, right, for these compute resources as much as we need, right? So the system behaves very much like a Kinesis client library, right? When we need more resources, we add more containers. Those containers grab indices. They're all the same size, right? So we know exactly how many we can fit in each container. And we keep going on as much as we need. We can also downscale it as needed. As you can see here, this also takes care of data isolation, right? Each tenant is physically isolated from the other and cannot impact performance of other tenants. There is some impact because of the shared compute as you can see even on this picture, right, of each container, but that's much lower impact than entire system being multi-tenant. We also, can encrypt each customer data with a different encryption key and providing additional layer of security. And finally, let's talk also about the retention, right? So let's say you have two customers that want to have different data retention. You can then partition that data also in time, right? And maybe every week you can create another partition, or even every 3 days. Now, after certain customer partition kind of runs out, right? The retention runs out. Maybe they want to keep data for a month. Then you simply delete the last partition. It's very simple and very, very efficient. And each customer could have different retention. So some customers, you will keep 4 weeks and delete the 5th week. For some customers, you will keep 8 weeks, delete the 9th week, and so forth. So before we move on, let me just recap with the final high-level architecture diagram. So we have a sensor sending data on the left, right, to the backend to some kind of load balancer. And then we have this first random Kinesis stream, right, a kind of a vanilla Kinesis stream, which we scale up and down as we need to. Then we go this partitioning, undergo partitioning layer, which does entropy reduction, and we push data into the second Kinesis stream, which has a physical partitioning by the tenant. And then after that, we pass it to our indexing layer, which takes each partition, stores it in a separate index. Indexing stores it in S3, and finally, those S3 indices are offered to another compute cluster, which exposes data through API for searching. So we have done this on very large scale. So we have tens of thousands of tenants today, and we have are storing tens of petabytes of data on S3 through the indexing process. We have millions of endpoints and tens of thousands of Kinesis shards. We ingest trillions of events per day, and our compute resources contain thousands of Amazon ECS containers. I will now hand Mike to Corey to go deeper into the partitioning logic.
Thanks, Davor. My name is Corey Leopold. I'm a staff engineer with VMware. At first, we thought the traffic per endpoint would be consistent enough that we could provision based on license endpoint, which is what we see here. We knew this was not perfect, but we thought we could live with some over-provisioning of our tenants and manually add capacity for a few outliers here and there. But what we realized is that it wasn't just a few outlier tenants, it was large variability in the traffic per endpoint that tenants sent us, as you can see in a graph on the right. This can be caused by a number of different factors. It could be a system administration tool deployed in the enterprise, or a different mix of OS types, or any number of other factors. Sizing all tenants for the tenants with the highest per endpoint traffic quickly became untenable, and we had to reduce our Kinesis costs somehow. In addition to the sizing challenges we just saw, we also have a few different rapid traffic profile changes we see in the tenant data. Some tenants do a nice smooth deploy where they add a few endpoints each day and their endpoints send consistent data. Others do a slow ramp up as a proof of concept and then sit at a certain scale for a while and then suddenly do a mass deployment. The third tenant scenario isn't a deploy, but usually some kind of configuration issue, like a firewall rule that disconnects a mass number of sensors from our backend. When this happens, our sensors start to store data locally. When the configuration issue is fixed, it floods the data into the backend, and eventually traffic volumes return to previous levels. We do scale the backend partitions, but we do scale back the partitions, but lazily. We can also see a similar traffic profile with enterprise software deploys. Our system should be responsive to, and more importantly, be resilient for each of these traffic change profiles. As Sai mentioned earlier, Kinesis has the ability for users to use explicit partition keys, and our architecture takes advantage of that feature. It helps me to think of the key space as numbers 1 through a 32-bit unsigned integer. Because we are now partitioning data by tenant, we need a way to map tenants to the key space. We accomplish this by using the first 11 bytes of the key to identify a specific tenant. Then we reserve the last 5 bytes of the partition key as a shard identifier within the tenant, allowing us to have multiple shards per tenant. You can think of this as each tenant having their own mini Kinesis stream. This has advantages over provisioning a physical Kinesis stream per tenant in that we don't have to dynamically provision logic as tenants come and go. It also allows us to use a single KCL app and a single cluster of workers to process all tenant data. As we saw in the previous slide, we reserve the last 5 bytes to further subdivide the tenant key space. Here we have a single partition key shard tenant that is now grown enough that we need to add another shard and start using another partition key. What happens is we split the shard, and our traffic mapper automation usually splits on the next partition key after the one we know we were using, because that one is very easy to find by adding 1 to the used partition key. Once the split happens, we inform our stream partitioning to start using the additional partition key for the tenant. Now the customer grows more, and we have to split again. Now the customer has decreased traffic a bit, and we have to merge the shards together and only use 2 partition keys. It is important to note here that in our case, we always use a single partition key in each shard. There is no limitation as to how much data can be written to a partition key up to the full limit of the shard. This slide pulls it all together. We have a front-end Kinesis stream that we write to in the typical Kinesis use case. Data is written to random partition keys, and the shard space is evenly distributed. Then we have a processor that sorts this data, formats it in a way our indexers can consume, and now writes the data to specific assigned partition keys that we have previously discussed. It also writes a bandwidth metric for each tenant so the Traffic Mapper service can calculate bandwidth needs per tenant. Once Traffic Mapper calculates each tenant's bandwidth needs and determines the number of partition keys each tenant needs, it then performs split and merge operations on the Kinesis data stream to ensure that each used partition key is on its own shard. Once that is finished, it then informs the partitioning service how many partition keys to use for each tenant. This allows us to index each tenant's data for the next processing stage into their own indexes, providing customer data separation. This is simplified to only show 6 shards, and in reality, if we were designing that small, we would just over-provision the shards and call it a day. But when you start talking about 20,000 shards in a stream, over-provisioning becomes a significant cost issue, and it becomes important to manage scale with automation. Here we show an example of a tenant that had a significant data surge, at least 7x or so for a short period of time, in this case from about 3:30 p.m. until 10 p.m. or so. What happens is data starts to back up the shards and partition keys assigned to that customer, but only the shards and partition keys for that tenant are effective, keeping this surge from causing a systemic issue for all tenants. On the bottom graph, we can see the effect of that. This is per shard iterator age, and we can just see a few shards belonging to a single tenant of the thousands in the system getting behind. Eventually, you can see these skips in the lines where it will add more shards and the shard ID changed, causing a new metric series to start. When we get enough capacity, the shards start to run back to the bottom, catching up. It does spread out a bit because in these large spike cases, Traffic Mapper has to add a lot of shards, and it can take a while to perform all the split operations needed. As you can see, some portion of this tenant's data was delayed indexing until 6 a.m. The architecture isolates customer data aberrations to keep them from having a systemic effect. This architecture in its early partitioning enables to scale to thousands of tenants of very different sizes, from tens of endpoints to hundreds of thousands. Using specific partition key ranges per tenant provides isolation not only in Kinesis, but in our downstream processing and indexing. The system is adaptive to different tenant traffic levels. Initially, the team we had developing this capacity was fairly small, about 7 developers from inception to first customer in about 1 year. We couldn't have accomplished this with a small team if we had to bear the burden of managing and operating a streaming infrastructure cluster. Like anything, there were a few enhancements we would like to see. At a certain scale, our limiting factor will become how many split and merge operations we can perform. Currently, this is limited by AWS, and each operation takes 8 to 15 seconds and cannot be parallelized. Our highest data rates are very weekday working hour specific, and currently, we don't scale Kinesis shards down for nights and weekends, but we would if we could split and merge faster. We have implemented an S3 offloading feature around KPL/KCL libraries, where if we were getting right throttled, we dump to S3 and then write much smaller messages into Kinesis on where to find the data until our traffic mapping process can scale. It would be nice to see this incorporated into the service. Given the amount of specific domain logic in our architecture, we have not open sourced this partitioning work yet. However, some of our teams have implemented a native Golang KCL with full parity with its Java counterpart. You can find it on VMware's GitHub. Thanks for your time, and I hope to see you around the conference.